You deploy a production retrieval-augmented generation pipeline into an enterprise environment. A user inputs a simple, high-stakes prompt: extract Q3 2024 revenue from a corporate knowledge base. A standard vector database processes this request by converting the text string into a numerical embedding. That embedding is then mapped as a coordinate in a high-dimensional space. This is a representation of that vector space. The query point for Q3 revenue is plotted here. To answer the prompt, the system retrieves its nearest neighbors based entirely on mathematical proximity. Notice the highlighted text chunks returned to the model. They contain data for Q2 and Q4. The system pulled Q2 and Q4 data because the language used to describe quarterly earnings is highly uniform. Mathematically and conceptually, Q2 revenue is almost identical to Q3 revenue. Factually, it is the wrong answer. When you ask an LLM to extract exact numerical figures based on these chunks, the model hallucinates. It confidently summarizes the wrong quarter, because the wrong quarter is all it was given. Traditional RAG pipelines fail in high-stakes environments because they conflate semantic similarity with factual relevance. Engineering teams have spent years trying to patch this flaw by optimizing embedding models, deploying cross-encoders, and refining chunking strategies. Those efforts have hit a hard ceiling. This chart tracks engineering cost against accuracy on structured documents. Notice how accuracy flatlines right at the 50% mark, even as the engineering effort scales exponentially. State-of-the-art vector RAG pipelines cannot reliably parse complex tables or nested structures. Breaking through this accuracy bottleneck requires abandoning arbitrary chunking and removing the vector database from the pipeline entirely. The alternative is PageIndex, a vectorless, reasoning-based retrieval framework. Treating retrieval as a deterministic reasoning problem rather than a probabilistic math problem is the key to unlocking near-perfect accuracy. To understand how reasoning-based retrieval works, we have to look at the most challenging retrieval environment in data science: densely structured financial and regulatory reports. U.S. Securities and Exchange Commission filings, specifically 10Ks and 10Qs, act as the ultimate stress test for any RAG architecture. They are long, heavily cross-referenced, and rely on nested data tables. A standard pipeline begins ingestion by running these filings through a naive text splitter. The text splitter ignores the document's logical layout and cuts the text based solely on a hard token limit. Watch the result of that process. The document is physically sliced into uniform, disjointed squares. Sentences, tables, and hierarchical relationships are severed. Before the embedding model ever sees a single word of text, the text splitter has introduced severe context blindness. Consider a financial table with a crucial footnote. Once severed by a token limit, the embedder analyzing the footnote chunk has no contextual awareness of whether that footnote belongs to the executive summary or a deep appendix. When these isolated chunks are retrieved and fed into an LLM context window out of their original order, they exacerbate the lost-in-the-middle phenomenon, where the model ignores critical context buried in a disjointed prompt. Any system that destroys document hierarchy during the ingestion phase is structurally incapable of precision multi-step data extraction. The PageIndex architecture solves this by rebuilding the ingestion phase from the ground up, mapping documents into a hierarchical JSON tree instead of flattened vectors. Instead of token-based text splitters, the system utilizes layout analysis and LLM-guided parsing to detect natural headers, subheaders, and thematic shifts in the text. This diagram illustrates the document reorganizing itself into a machine-readable format. A single root node branches recursively into chapters, and those chapters branch into specific sections. This structure effectively acts as an intelligent, dynamic table of contents that an LLM can parse and understand. Because the segmentation is semantic, the raw text inside these sections is preserved as contiguous blocks. There are zero arbitrary token boundaries splitting the information. This JSON tree is incredibly lightweight, especially when contrasted with the massive storage and compute requirements of maintaining millions of high-dimensional embeddings. By maintaining strict hierarchical context right from the ingestion phase, the system allows the LLM to navigate a document's true architecture rather than searching blindly through a bag of random text strings. To see how the LLM navigates this architecture without exhausting its context window, we have to isolate the microstructure of the reasoning tree. This is a focused view of a single functional page index node. It is built on specific key value pairs, the node ID, title, summary, and subnodes. The title and summary keys serve as highly condensed representations of the section's actual content. The subnodes key establishes the strict parent-child relationships, creating the MAC required for vertical navigation through the document. The node ID acts as a unique pointer. It exists solely to fetch the raw, untouched text from storage, and it only triggers after the LLM explicitly selects this specific node. This JSON anatomy is efficient. An LLM can evaluate a section's exact relevance instantly by reading the summary, without wasting valuable context window tokens reading the raw data inside it. Once the tree is built, the architecture moves to phase 2, reasoning-based retrieval. The LLM receives the user's prompt alongside the JSON tree's titles and summaries. Crucially, the raw text is held back. The logic applied here mirrors game theory tree search. In 2016, DeepMind's AlphaGo defeated Lee Sedol not by calculating every single possible board state, but by evaluating and navigating only the most promising branches of possible moves. The retrieval LLM does the exact same thing with the document. It evaluates the most promising branches of the text based on the user's prompt. If we run our original query, find Q3 revenue, the LLM reads the root node, identifies financial statements as the correct branch, traverses down to revenue analysis, and finally selects the Q3 subnode. The system operates on an iterative loop. If a node summary reveals it doesn't contain the answer, the LLM backtracks up the tree and selects a different branch. For the final retrieval step, the system uses the selected node ID to fetch the contiguous raw text block. That context is then passed to the model to generate the final, factually accurate answer. This method natively resolves semantic mismatches. A vector database might miss a section titled Risk Factors if the user searched for Main Dangers. An LLM reading a structural tree understands immediately that Risk Factors is the logical place to look. Active logical navigation to a specific node guarantees high-precision retrieval. Blind spatial proximity simply cannot replicate it. We can measure the impact of this architectural shift by looking at the empirical benchmark data. FinanceBench is the industry standard for evaluating financial document QA. It requires exact numbers extracted from real, complex SEC filings. This chart displays the results. The baseline vector-based RAG achieves roughly 50% accuracy. The MOFN 2.5 system, powered entirely by the Vectorless PageIndex framework, achieves 98.7% accuracy. That 48-point gap represents the difference between an unreliable prototype and a production-ready enterprise tool. There is a secondary engineering benefit here. Because the LLM navigates the document and outputs exact node IDs, the retrieval path is fully audible. You know exactly which pages and sections informed the answer. This capability officially eliminates the black box of vector proximity, fulfilling strict compliance requirements for enterprise environments. Pivot to the pragmatic engineering reality. Every architectural shift introduces new trade-offs. This matrix compares operational costs. Vector databases provide fast, cheap, broad search. PageIndex offers deep, traceable search, but carries a latency penalty. Navigating the JSON tree requires multiple LLM calls, increasing response times and costs. It's a precision tool, not a replacement for high-volume search. In practice, the future of enterprise RAG relies on hybrid systems, deploying vectors to quickly filter massive datasets down to the right document, and using PageIndex for the final, precise extraction. Scaling RAG accuracy requires moving beyond vector math. High-precision extraction depends on identifying the exact moment where search ends and logical navigation begins. Thank you for watching. If you want to explore the code, the open-source PageIndex documentation is linked in the description below.